Okay. All right. So, last time we talked about the exponential map, right? And we proved this proposition at the end that if you take a normal ball in your Riemannian manifold, so that means the image of a ball in the tangent space such that the exponential map at P restricted to that ball is a diffeomorphism, then the images of straight lines through the origin under the exponential map, those are geodesics passing through P. Those geodesics are shortest length curves in that ball. So for any point in that ball, in the normal ball, the geodesic from P to that ball is the shortest length curve in the whole manifold, from the point P to the point in the normal ball. Right? This is what we proved at the end of last time. Yes? So any questions about this? So this says that geodesics are locally length minimizing, right? Locally, they are length minimizing. Locally, they are the shortest length curve between 2 points. Is this clear?
Yes.
Yes, sir.
Right. So if I take any geodesic and I take a point P on it, so geodesics are locally length minimizing. So that means that if gamma from an interval AB to N is a geodesic, then for all T naught belonging to AB, there exists epsilon positive such that for all ST belonging to T naught minus epsilon, T naught plus epsilon, gamma restricted to the interval ST is the shortest curve in M from gamma S to gamma T. Okay, so here's the picture. Here you have T naught, which is gamma T naught. So I can call this P. And here you have let's say R is equal to gamma T and Q is equal to gamma S. So then this is the shortest length curve. This geodesic is the shortest length curve from gamma S, from Q to R. So that means, in other words, the length of gamma restricted to ST. So is the unique, I should say, is the unique shortest curve. Length of gamma restricted to ST is equal to the distance between gamma S, gamma T. Where remember the distance between 2 points was the infimum of the lengths of all piecewise C1 curves in M joining the 2 points, right? So is this clear? So we didn't prove exactly this. We proved that if I take it from P up to R or from P to Q, then the geodesic is the shortest length curve, right? So here we're making a slightly more general statement that if I take any points Q and R in the neighborhood of P along the geodesic, then the geodesic is the shortest curve joining those 2 points, right? We're making a slightly more general statement. Is it clear? So we're going to prove this statement. So for this, we need what's called totally normal neighborhoods. So remember that a normal neighborhood of a point P was the image of an open set around the origin in the tangent space under the exponential map, such that the exponential map restricted to that open set was a diffeomorphism onto its image, right? That was a normal neighborhood. Now what we want to say is, given any point P, we can find a neighborhood W of it, which is a normal neighborhood of each of the points in W. So that will be called a totally normal neighborhood. Okay, so W is a normal neighborhood of each point in W. All right. So let me give you the precise statement of the theorem. So given a point P in M, there exists a neighborhood W of P and a delta positive such that for any point Q in W, the exponential map is a diffeomorphism on the ball of radius delta inside the tangent space in Q, right? So Q is varying throughout the neighborhood W, and the exponential based at Q is a diffeomorphism on this ball, B delta 0 in TQM. And the image of this ball, B delta 0, under the exponential based at Q, this contains W. So therefore, W is a normal neighborhood of Q as well for all Q in W. Okay. So hence, W is a normal neighborhood of each of its points. Okay. So let's prove this. So given P and M, so we want to show there exists W neighborhood of P and delta positive such that for all Q in W, X Q from B delta 0 in TQM to its image in M is a diffeomorphism and W is contained in X Q of B delta Z. Okay, so let's prove this. So is the statement clear? So let epsilon positive be such that X from a neighborhood of an open set in the tangent bundle epsilon positive and U a neighborhood of P is defined. So we saw that the exponential map was defined in open sets in the tangent space of this form. So U was of the form tangent vectors Q comma V, where Q belongs to U, which is a neighborhood of P. V belongs to TQM, and norm V is less than epsilon, right? Yes? Okay.
Yes.
So now define a map capital F from U in Tm to M cross M Q comma V maps to so the first point is just Q and the second point is XQ of V. So let me draw you a picture. So here's the neighborhood U, and the map is the following. I take a point Q and I take a tangent vector V at Q, and then I follow the geodesic with initial condition V up to time 1, that is the exponential map, and this point is XQ of V. So what we want to show is that if you think about it, if we were doing this in Rn, right, what would this map be in Rn? I'm just taking a point and a vector in Rn, and I'm following the vector for time 1, right? I'm just adding the vector to it, right? Following the vector. So yeah, I mean, in Rn, this map would be in, what would this map be in Rn? It would be QV goes to Q comma Q plus V, right? And so this map is a linear map, right? And what is the matrix of this linear map? It is identity, a block matrix, identity, 0, identity, right? Right? Is this clear?
Yes.
Yes?
Yes, sir. Yeah.
Yes.
Because this first row would be the first component. So that's Q and V. So you'll have identity here, right? If I multiply this by QV, right? F of QV is this into QV.
It should be I0, II, right?
Yeah, it should be the other way around. Okay, fine. All right, yeah, it's the other way around. So, okay, so yeah, if I put the V on top and the Q below, then it's this way, right? So anyway, okay. So yeah. Sorry. This might confuse you a bit for what we're going to do. But anyway, you can see this map is invertible, right? Yes, this map is invertible.
Yes.
So what you would expect in a manifold is that this map in a neighborhood of the 0 vector in the tangent space at P, there it should be invertible. And what is the one way we know to show that a map is locally invertible? How do we show it?
Derivative is invertible at a point.
Right, the inverse function theorem, right? We just want to use the inverse function theorem. So we want to calculate the derivative of this map at a point at the origin in the tangent space at P. So this, let me write this as F1 of QV, comma F2 of QV. Okay. See, why is this map invertible? Because basically, if I give you a pair of points in this ball, suppose we were in Rn, if I give you a pair of points in this ball, then there's a unique, I mean, the starting point is determined. So the Q is determined by this Q, and the vector is determined. It's the unique, it's just the starting point, end point minus the starting point, right? That gives you the vector V, right? So you should expect that in a Riemannian manifold, locally, for every pair of points, the first point is given to you, and the vector will be uniquely determined by the other point. Is it clear? The vector V will be uniquely determined by the other point. Do you understand what's happening? Right? Okay, so let's calculate df at the point P0. So this is going to be what? This is going to be a block matrix df, sorry, df1 at P0, df2 at P0, okay. And this is going to be from where to where? This is going to go from, so we have to see what is the tangent space to the point P0 in the tangent bundle. Right, now remember, in the tangent bundle, we had coordinates. If I chose coordinates x1 to xn near P, then I got coordinates for the tangent bundle x1 to xn and y1 to yn, right? Where yi's were just dxi's, okay? And so our the tangent space to the tangent bundle was spanned by del del x1 to del del xk. and by del del y1 to del del yk, right? Now, what is, so del del x1 to del del xk, those are a basis of the tangent space at P, all right? Yes. And what about del del y1 to del del yk? Well, y1 to yk, those are coordinates. If I fix the point P and I vary the vector v, then the x1 to xn coordinates stay fixed and the y1 to yn coordinates vary, right? So the y1 to yn, those are coordinates on TPM for a fixed x, right? And so there, del del y1 to del del yk, those will be a basis for the tangent space to the tangent space at P, right? Which is again identified with the tangent space at P. So that means del del x1 to del del xk, those span TPM, and then del del y1 to del del yn, those also span, I mean, the tangent space to TPM, which is identified with TPM. Okay, so this is therefore the tangent space to the tangent bundle is identified with the direct sum TPM, direct sum TPM. And where are we taking values? We're taking values in M cross M. The tangent space to M cross M is clearly identified with TPM cross TPM, right? Is this clear?
Yes. Yes.
Because what is the image of P comma 0? P comma 0 maps to P comma P, right? P comma 0 maps to P comma P. So the tangent space to M cross M at P comma P is TPM direct sum TPM. So this becomes a self map from TPM direct sum TPM to itself, okay? Now we have to calculate its derivative. So for that, the derivative of df1, this will be the partial derivatives with respect to the two variables Q and V in the first row, right? So what is the partial with respect to Q? It is just identity. So I get identity here. Now, what is the partial of df1 with respect to V? It is 0, right? Yes?
Yes.
Okay. Now, what about df2? So the partial of, so f2 is xq of V. So the partial, when I fix, partial means I have to fix V equal to 0. I have to fix V equal to 0 and differentiate in Q. So if I put V equal to 0, then this x Q of V becomes just Q, right? So then it becomes just the identity map of M. So the partial with respect to Q is again just the identity here. Okay. And now finally, I have to put Q equal to P and differentiate with respect to V. So if I look at xp of V, the derivative of that at when V is at the origin, that is the identity map again. So I get exactly what I had in Rn. I get the same block matrix, identity 0, identity, identity. Is it clear?
Yes.
Okay, so we're using the fact that we proved earlier. The derivative of xp at the origin is the identity map from TPM to TPM. All right, that's used to calculate this last diagonal entry here using this fact. Okay, is this all right? Hence, DF is invertible at P0. So by inverse function theorem, there exists a neighborhood U prime in the tangent bundle, U prime of P0 in Tm. So U prime is equal to a neighborhood of the form QV. Q belongs to V prime. V belongs to TQM. Norm V is less than delta. For some neighborhood V prime of P in N and some delta positive, such that F from U prime to W prime, which is a neighborhood of P cross P, P comma P in M cross N, is a diffeomorphism. For some neighborhood W prime of P comma P in M cross N. All right. So now you choose, we can choose W, a neighborhood of P in M, such that W cross W is contained in W prime, right? We can do this. Now,
Yes.
now let Q prime be in W, be 2 points in W, then Q comma Q prime, this is a point in W cross W, so this I can write as F of some Z comma Q, Z comma W, sorry, for some ZW in this U prime. So what is F of ZW? It is Z comma X Z of W for some ZW in U prime. But that implies that if you equate the first coordinates, that Z is equal to Q and Q prime is equal to X Q of W, where W belongs to TQM and norm W is less than delta. So therefore this implies that this is true for all Q prime in W. So this implies that W is contained in Bx per Q of B delta 0 for all Q in W. And also B delta 0 is contained inside U prime or maybe I should write it like this. So and Q singleton Q cross B delta 0. This is contained inside U prime. And F restricted to Q. So maybe I should say so. This is a diffeomorphism onto its image because it's a restriction of a diffeomorphism. And F of QV is equal to Q X QV. So if this is a diffeomorphism, here Q is fixed, only V is varying. Thus, XQ restricted to B delta 0 is a diffeomorphism. Is this clear? Onto its image. Okay, so that finishes the proof. Is this clear? Yes?
Yes.
Yes, sir.
Any questions? So what is the picture that we have now? So we get this totally normal neighborhood. So what is the picture? The picture is basically we get this W and now the point is if I take any 2 points in this neighborhood, say Q and R, then I know that W is contained in the image under the exponential map of the ball of radius delta in the tangent space at Q, right? So that image will contain the neighborhood W. So this dotted ball is the X Q of B delta 0. This contains W. And here in this ball, I know that the geodesic from Q to R, I have a geodesic from Q to R. This is the shortest length curve in the whole manifold, right? So that means that any 2 points in this normal neighborhood, Q and R, are joined by a unique shortest length geodesic. Is it clear? Okay, so we have less than a minute. So let's stop here and then we'll start again. All right, let's stop now.